Hi guys. Okay, so chapter 6, we are continuing further, but before we get into writing the formulas and the nomenclature, let's do a review of what was covered last week, which was basically in theory. So we talked about the ionic compounds. The ionic compounds are made when the metal and the non-metals react. The metals are going to form a positive charge. The non-metals form a negative charge. And then there is another type of compounds, which are called the covalent compounds. These are formed by the sharing of the electrons. And normally we see non-metals forming covalent compounds. Okay, so what is the rule that defines whether an atom is going to lose electrons, gain electrons, form an ionic bond by the transfer of electrons, or they are going to form the covalent bonds also by the sharing of electrons, and that is the octet rule. Octet rule is 8 electrons in the last shell. The last shell is called the valence shell, and that valence shell, the number of electrons that it contains, so the whole idea is either to get 8 electrons in the last shell, which is by gaining, losing, or by sharing. Okay, so the rule of 8 electrons is one piece which relates to the nearest noble gas configuration except helium. Except helium, because helium doesn't follow the octet rule. Helium only needs 2 electrons, or it has only 2 electrons. Okay, then we have the electrons also present in the last shell of the transition and the post-transition metals. These are the d block elements. So these d block elements, they have, because d block, they have the d orbitals, and these d orbitals can hold a maximum of d orbitals can hold a maximum of 10 electrons. Okay, so as a result, the 8 rule, it doesn't apply on them. So what applies on them? The half filled and the full filled. So the whole idea, the elements that are in the d block or have the d orbitals, with them, the rule is that they can lose electrons in order to get half filled orbitals. In other words, 5 orbitals, or 3 orbitals, like the 5 electrons in the d orbitals, or 3 electrons in the p orbitals, or 1 electron in the s orbital. So either get half or get fulfilled. So when they are half filled and fulfilled, then they are more stable. Okay, so now this is a very general rule that applies to the charges and the bonds on the groups, the elements that are present in these groups. So group number 1, group A, group 1A, it has 1 valence electrons and it will form +1 charge. That means it will lose 1 electron. So lithium, sodium, potassium, rubidium, cesium, francium, these guys will lose 1 electron. Then group 2A has 2 valence electron and it loses 2 electrons. And the number of electrons that are lost or gained, that determines how many bonds are going to be formed. So if an atom loses 2 electrons, it will make 2 bonds. If an atom loses 3 electrons, it has 3 valence electrons. That is, we are talking about group 3A. Generally aluminum here. So aluminum has 3 valence electrons. It will lose those 3 valence electrons and it can make 3 bonds. Now, interesting thing is this group, which is the group 4A. Group 4A has metals, non-metals, and metalloids. Okay, and the non-metals here is carbon. So because of that, the metals always lose electrons, metalloids can also lose electrons, but the non-metals will always share. So anyways, all the elements that are present in group 4A have 4 valence electrons. That is the 4 electrons present in the last shell or the highest energy level. Okay, then they can lose electrons, so they will have +4 charge. Or these atoms in group 4A can gain 4 electrons, they'll have -4 charge. And as I mentioned, the non-metals, which is the carbon is going to form bonds by sharing. Okay, so that is why the whole situation in group 4A is variable. Okay, now let's look at the elements that are present in group 5A. 5A, 6A, 7A, and 8A, these guys are all these guys are all non-metals. So non-metals present in group 5a have 5 valence electrons. And how many more electrons do they need to get 8? That is 3 more electrons. So when you gain electrons, you get a negative charge. And since 3 electrons are gained, minus 3 charge, plus, so the 3 bonds are formed. 6a, 6 valence electrons, negative 2 charge, only 2 bonds are formed because 6 plus 2 is 8. So you see that the elements that are present in group 5a, 6a, 7, and 8a, or basically 5a, 6a, and 7a are very close to 8a. And 8a is a noble gas. Noble gases have 8 valence electrons. They are not going to form any bonds, no charges, depending upon the conditions. Okay. Now comes the group 7a, 7 valence electrons, and only need 1 more electron to get the nearest noble gas configuration, or the 8 electrons. So they will make only 1 bond. But there are exceptions. Exceptions are that, first of all, the metals that can form more than 1 type of positive charges. These are the transition and the inner transition elements. So we see that the transition elements, the D block and the D and the F block, basically these D and the F blocks, these guys can make more than 1 type of positive, but the F block is not very, common. So that's why we don't just ignore it, like for this course at least. So we are going to just look at the metals present in the D block, which can form more than 1 type of charges. Now, first of all, how do we represent them? +1, the charges are represented by the Roman numerals. So commonly, +1, +2, +3, +4, +5, +6, all those are represented as Roman numerals. Okay, so Roman numeral 1, as you can see, 2, 3, 4, 5, commonly these are the ones. So how do we write them is in this format. And there's also another thing. The lower plus charge and a higher plus charge, besides the Roman numerals, there is other method of forming their names. The lower, so this is the oxidation state. These are called the oxidation states. So whenever there are more than 1 type of charges, these are called the oxidation state. So the lower oxidation state is going to end in us, and the higher oxidation state is ending in -ik. The lower in us. So you see copper +1 and copper +2. So lower oxidation state, cuprous, higher oxidation state, cupric. Iron, similarly, lower oxidation state is +2, higher oxidation state is +3. So lower oxidation state is ferrous and higher oxidation state is ferric. So you should not get confused that every time us is going to be lower and ik is to be higher. No, the us and ik applies with respect to the specific atom. So here copper +1 is cuprous, but iron +2 is cuprous. Copper +2 is cupric, but iron +3 is ferric. You see that? So this is and ek is with respect to the specific element. Okay, so this is one thing. Then comes the non-metals. If the non-metals are just bonding to themselves, like are just bonded to the metals, bonded with the metals, not to themselves, but bonded with the metals. So non-metals and the metals. In that case, their naming is ending in IDE. Don't forget that. It's very important, IDE. Okay, non-metals, if they combine to themselves, then also it would be IDE. Sorry, no, then there is no name, then it's just their name if they combine to themselves. But if they are bonded with oxygen or other non-metal with a higher electronegativity, then they make polyatomic ions. Okay, so polyatomic ions are formed because non-metals have very strong, bonding capability is more. Some of them, not all. So for example, let's look at it. Group 1A, Group 3A, Group 4A, Group 5A, Group 6A, Group 7A, and Group 8A. all of them contain nonmetals. So the nonmetals that are present in group 1A, nonmetals that are present in group 1A is just hydrogen. So hydrogen, is just going to be, is just hydrogen. So just 1 + 1 charge, 1 bond, and it's not just one charge. Sometimes it does not form, sometimes. So sometimes. So when sharing electrons, then no charges. So that is also a possibility. So we will study that today. Okay. Then comes the group 3A. So again, group 3A, 3 valence electrons, 3 bonds like in boron. So these are formed by sharing. So that is covalent bonding when you're sharing. Okay. Next is carbon. A carbon can form +4, -4, and it can also form sharing. Okay, but it's still going to be only 4 bonds. Silicon, again, 4 valence electrons, 4 bonds formed by sharing, so forth. So we leave that. Now look at group 5A. That's where we start seeing the differences. If you look at nitrogen and phosphorus in group 5A, 5 valence electrons will have -3 charge. And sometimes when it's forming ionic bonds, yes, then it is -3 charge. But when it's covalent bonding, then just keep this in mind, then no charge. Covalent is bound by sharing. So for the sharing, there are no charges. Okay, so they will just form the bonds, 3 bonds. But phosphorus has a capability to make more bonds, 5 bonds also. Look at oxygen and sulfur. Sulfur and oxygen have 6 valence electrons, and fine, they can have -2 charge. They can make 2 bonds, and when they can make again ionic and the covalent bonds. So all this applies, to every element. But again, sulfur can make 2 bonds, but sulfur can also make 3 bonds, 2, 4, and 6 bonds. So 2, 4, and 6 bonds sulfur is making. Look, group 7A. Fluorine, chlorine, bromine, iodine, fine, 7 valence electrons, they'll make 1 bond only, but chlorine, bromine, iodine can also make 3, 5, and 7 bonds and 1 bond. So normally 1 bond is all, is normal conditions. Now look at these group 8A. Group 8A, helium, neon, argon, xenon, krypton, radon, no bonds, right? But xenon has the capacity to make 2, 4, and 6 bonds. Okay, now what are these exceptions? These exceptions are when these nonmetals react with another element which has a higher electronegativity. Okay, whenever they are connected with higher electronegativity, and generally with oxygen. Okay, generally with oxygen. So we see a lot of, like, all these are polyatomic ions. Polyatomic ions. So they can make these polyatomic ions called PAI. Okay, and that happens when oxygen combines with sulfur, and then it can form sulfur dioxide, sulfur with 2 oxygens, sulfur with 3 oxygens, sulfur with 3 oxygens with a negative charge, sulfur with 4 oxygens with a negative charge. So all these species are possible because sulfur can make more than one type of bonds. Similarly, look at this PO3, 3 negative, and PO4, 3 negative. Okay, so again, expanded capability, same is the case with the chlorine, bromine, all these. Whenever they combine with oxygen or any other element with a higher electronegativity, then they will be using their expanded capabilities. So there is a trend in the periodic table. When we talk about electronegativity, what is electronegativity? Electronegativity and electron-affinity go side by side. Electronegativity means love for electrons, or the ability to attract electrons, ability to attract electrons. So when you go from left to right, the electronegativity increases, right? And it's happening in the same period. But when you go from top down, when you come from top down, okay, then the from top to bottom, then the electronegativity decreases. And electronegativity and electron affinity go side by side. So in other words, if you look at it, the non-metals have non-metals versus metals. So metals have a lower electronegativity value, and non-metals have a higher electronegativity value. Okay. All right. So these values are present on page 8, and you're going to be using them anyways, you know, when you do these polarity in the molecules. So just keep this in mind, that these electronegativity values have been verified and tested, and we have obtained them going from 0 to 4. So we see that the elements that are metals usually have like much less than like 2, you know, it's like 0.4, 0.3, 0.5, 1, something like that. But the non-metals will all have the electronegativity which is closer to 4. Okay, so these are the things, and then we are going to study about the bonding, you know, whether it's a polar bond or non-polar bond. Okay, now let's look at the polyatomic ions by themselves. Now, polyatomic ions, as we talked about, they are made of 2 or more atoms. Okay, so these are just some of the examples. Now, here's a very important point with the polyatomic ions. They are very specific to the main, you know, atom, and then you see oxygen is being added to nitrogens, to sulfur, so phosphorus, and here oxygen, all of them connected to oxygen. Besides that, like I said, it's 2 and more. So here is this 3: hydrogen, carbon, and oxygen, hydrogen, sulfur, and oxygen, hydrogen, phosphorus, and oxygen, chromium and oxygen, 2 atoms of chromium and 7 of oxygen. So it's like that. Okay. Now, here's a very important pattern. You see this 8 versus 8. So it is not either. It is 8 versus 8. So 8 is a lower oxidation state. Lower oxidation, lower number of oxygen atoms, you can say, lower number of oxygen atoms. And 8 is higher number of oxygen atoms. And where is that? This is 8, and 8 is with respect to 1 atom, you know, 1 atom only. So single atom. So these go like, these are with respect to 1 atom only. So for example, you see nitrogen in a lower oxidation state, less oxygens, 8, more oxygens with respect to nitrogen, 8. Next, look at sulfur, less number of oxygens, 8, more number of oxygens, 8. So when it's 3 oxygens connected to sulfur, then it is sulfide. But when it's 3 oxygens connected to nitrogen, then it becomes 8. Because nitrogen has a maximum capacity to hold 3 oxygens. It cannot go more. But sulfur has a maximum capacity to hold 4 oxygens. So in that case, the maximum capacity of nitrogen with 3 oxygens is nitrate. And with sulfur with 4 oxygen is sulfate. So you see 8 and 8 is with respect to the single atoms. Now look at phosphate and phosphite. So we have phosphate and phosphite. So 3 oxygens is phosphite and 4 oxygens is phosphate. So that's you know, this thing. Now look at the chlorine. Now chlorine, initially we found that chlorine could connect with maximum of 3 oxygens only, but we see that the chlorine is also capable of connecting with 2 oxygens. So when it's capable of connecting with 2 oxygens, chlorite, 3 oxygens, chlorate. But later on, we discovered that chlorine has a capacity to combine with 4 oxygens, and chlorine also has a capacity to combine with just 1 oxygen. So then we can't change the name to chlorate to ClO4. We said, okay, we need to find something else. So that's where these prefixes perchlorate and hypochlorite came into being. So chlorate, perchlorate means the maximum higher than 8, and hypo is lower than 8. Okay, so these are just the naming, you know, the naming in the naming you should recognize those sequences. Okay, then we have carbonate. So carbonate, you know, carbonate, but whenever you add bi, it means hydrogen. Anytime you have bi, it's hydrogen. So bi stands for hydrogen. So just keep one thing in mind, that carbonate has 2 negative charges, but the moment 1 hydrogen is added, that 1 charge is reduced. Same is the case sulfate, 2 negative charges. You add 1 more hydrogen, it becomes only 1 negative charge. Here, phosphite is 3 negative charges, but 1 hydrogen is added, it becomes 2. So here, let me write this down. Carbonate minus 2 charges. So this is carbonate, and we have plus 1 hydrogen ion, then it becomes HCO3 minus 1, and this becomes bicarbonate. Okay, so that's how it is. Okay, then the chromate and dichromate. The dichromate refers to these 2 chromiums, but just the chromate is you know that. So here, don't get confused. This is CO4 should be chromite, and this should be, you know, it's not. So some of the nomenclature was older, it got its name, you know, so just it stuck to it. Okay, next is when the nonmetals are combining to themselves, just by themselves, but without charges. So in that case, we use monoditritetra. So that's, we never use monoditritetra to the negative, to these, you know, to the metals. Okay, now we already talked about how the ionic bonds are formed and the, you know, these orbital diagrams, and now we are looking at the writing the formulas and the names. So let's start that now, writing the formulas and the names. So first of all, let's do this, writing okay. Now here, first of all, let's do one that we have simple, you know, you guys have the worksheet to do also on the naming. So just make sure that you know, you understand this, and I'm going to refer to the tables that are in the worksheet. So just give me 1 minute here. Okay, let's do a very simple naming. So you have sodium and you have chlorine, a very simple name, right? You've already known this name. I'm just starting with that. So there are a few things here you have to, when you write the naming. So always, first of all, identify the group number. Start with doing that. Identify the group number. Okay, and that gives you, that's one piece, first step. Second step is identify the charges on the group number. Okay, next is also check for variable valence state, and these are generally the D block elements. If there are D block elements, let me just put this here, for D block elements, Okay, for D block elements, check for variable charges. And where are you going to check? In the table, in the handout. So I have given you this handout. You guys should actually have this printed out. And this in this handout, there is the table, which is on page 5. Table, this is table 6.5, page 5 of handout. And you should be adding this on your own. Okay. Because that is going to give you, what is the oxidation state. Then comes the number 4 is look at the Roman numeral. Because that Roman numeral tells you that Roman numeral relates to the charge. Okay. That relates to the charge. And then put charges. Oh, sorry. Then there's something else also. Number 5 is the, then look at the polyatomic ion. Okay. Polyatomic ion, and then put charges. If there is a polyatomic ion or not. Okay. And then put the charges on top. Okay. Now, okay, so here I'm showing you on your handout. If you look at it on your introductory module, you will see, on the left-hand side with reference Chem 30A handout. So make sure you print this out. If you don't have it, this is the information you will need to do the worksheets. I mean, besides that also, you can use this handout on the exam. So anyway, so here is this handout. These are the metals already given to you. You can add more from your side, as you see, as you go about, like, you will see some information in the book. This is obviously from the book, but you can get it also from your worksheet. Anyways, so this is the handout, and which contains this some metals with more than one positive ions. And you see all these number of the Roman numerals and that relate to the charges. So that's one thing. Then comes the numerical prefixes like di, tri, tetra. So this is for the non-metals, when we are naming the non-metals. Then the diatomic molecules, their names are just their names as they are. And that this is a place where you will get the electronegativity values, which you will use later on. But there is also, I'm just trying to see where are the polyatomic ions, a list of polyatomic ions I have. Okay, okay, right here. Okay, here are the polyatomic ions. Okay, so this is table 6.7. and the names and the common polyatomic ions, but you can add more from your side also. So this is table 6.7, and I think this is page 6. Okay, so polyatomic ions are here. The method, the flow chart to do the naming is also here, which you can refer to. I don't, I generally don't follow that, but I follow my own thing here, which I'm teaching you. Okay, so this is the next page you will need. So 5 and 7 pages, at 5 and 6 page, at least you need to know that. Okay, now let's go back to here. So we are going to look at, I forgot which was that page again. 6.7, page 6. Okay, look. You should ideally memorize the polyatomic ions, but in case, so look at the polyatomic ions on page 6 in the handout. Okay, and this is table 6.7, and you can do it, you can also add from the other thing. Okay, anyways, let's move forward. Okay, so we got, and then put the charges. So polyatomic ions, we put the charges. We looked at the elements with the variable valence state, we put the charges, and then the group numbers, based on the very first, table we have here. On that, you put the charges and then put group numbers and then identify the metals and identify the non-metals. And remember that metals will have positive charge, non-metals will have negative charges. Okay, so you put the charges on top. Okay, then once you put the charges, then crisscross. This is easy. Crisscross the charges. Okay, now do not bring the charges, crisscross the numbers on charges. Do not bring the charge itself, like charge of plus or minus. You don't do that. And do not bring the number 1. Okay, but and then 7, 8 is if the subscript, so this is going to be crisscross the numbers and the charges and then bring them as the subscript. Okay, then if the subscript is more than 1, then put in parentheses. Okay, so let's do this now. Okay, so here we have sodium. Sodium is in group. So for the group, I'm going to just put here. So identify group 1A. Okay, chlorine is in group 7A. Group 1A and 7A. So that means sodium will have a +1 charge. Chlorine has a -1 charge. And where do you see this? This is very first thing here. So, you will have to make the notes of your own also. Otherwise, you can also refer this to the worksheet. This is also present in the worksheet. In the tables, all these tables are in the worksheet also. So you can use also, attach that worksheet to your handout. All right, so here we have now the writing the formulas and the names. So sodium is +1 charge and chlorine is -1 charge. Next is you're going to put these charges on top. So chlorine +1 and chlorine -1, sodium +1, and we crisscross. Remember, for 1, we don't write. We don't write plus and minus. So in other words, +1 and -1 cancel each other out anyways. So +1 and -1 cancels out. So therefore, what do we get? We just get NaCl. For the, remember, for naming metals, their names as is. Okay, for the metals, but name is as is, or if they are metals with, metals in the D block, then you add the us and ik, or you put the Roman numerals. So those things. Okay, for D block elements. Okay, and if it is just the nomenclature as we talked about with just the chlorine by itself, it's not like chlorine is not a polyatomic ion. So the name is sodium chloride. Okay, so that's one piece. Now let's look at another one, number 2. And here, let us say we have magnesium, Mg, and oxygen combining together. So let's write the names here, group numbers. So here the group number for magnesium is group 2A, right? You need to look at the periodic table. You will see magnesium is in group 2A and oxygen is in group 6A. So what are the charges on what is the charge? CHARGE. Charge on magnesium is +2. Charge on oxygen is -2. Okay, so we have +2 and -2 cancelled out. So what does the formula become? So if you write here Mg +2, oxygen -2, and even if you crisscross, this comes here, crisscross. So this becomes Mg2O2, but you cancel and simplify, simplify. You have to simplify. So this becomes MgO. And the name, because it's magnesium, just the metal, so that name doesn't change. This is magnesium, and the oxygen becomes, it's just oxygen by itself, oxide. So you see oxygen, so this is ide, and this is also, this is chloride. Okay, now let's look at another example. Here you have aluminum. Okay, here you have, let's say, aluminum combining with sulfur. Okay, so aluminum group 3A, sulfur group 6A, charges aluminum +3 charge, sulfur -2 charge. And again, this is all reference to the table that we have in the in this notes here. Also, if you look at it in the handouts, not in the handout, but it's also in the binary. It's actually in the handout also, but it's also in the worksheet. So otherwise, you need to memorize. Anyways, so now let's put this charges here. So for aluminum, +3, sulfur -2, and now you crisscross. This number comes here, this number comes here. So 3 and 2 don't cancel each other because two different numbers and they're not multiples and so forth. So with the name is, so this is Al2S3. Okay, and what is the name? Aluminum becoming the metal is, the name doesn't change, aluminum, and sulfide, SULFIDE. Okay, let's look at another one. 4. Here you have, let's do boron B combining with nitrogen. Or oxygen, let's do oxygen. Or actually, we did one over there. Let's do boron with nitrogen. Okay, boron with nitrogen. So group number of boron is boron 3A, nitrogen 5A, charge on boron +3, charge on nitrogen -3. So here you are putting the boron +3 charge, nitrogen -3 charge. So these charges +3 and -3 cancel out because you need to simplify. Okay, so that's why. So you simplify. So when you crisscross, this number comes here and this number comes here, and you're going to get boron Bn, just Bn. The name is, B stands for boron, and nitrogen is just by itself nitride, IDE. Okay, let's look at an example with 4, 5, iron. Okay, iron 2, chloride. And here you have iron 3 chloride. Okay, so here this means, remember that this means iron is in +2 state. This means iron is in +3 state. So this becomes iron stands for Fe, and +2. This means +2. This means iron +3. Chlorine is chlorine. Symbols, remember, memorize the symbols, okay? Now chlorine is group 7A. Okay, therefore charge on chlorine is -1. Group 7A, charge is -1. Charge is -1. So what do you get here? You get Fe +2 Cl -1. Here you have Fe +3 Cl -1, and you crisscross. So bring this here, bring this 2 here, and 1 will also be brought here, but we do not write 1. We do not write for 1. Okay, when we bring that charge. So, and remember, I'm not bringing in the plus and the minus. I'm just bringing in only the numbers in the subscript. So this here. So crisscross. So now we have what? We have Fe. For 1, we don't write. So Fe, so for chlorine. So FeCl2. And this becomes FeCl3. Okay. Now, FeCl2 is not going to be iron dichloride. So this thing is this. FeCl2 is shown as that. And iron chloride is this. Now, another question can be asked, what is the other name? So the other name is, because it's a lower state, this is a higher state, +3, +2, +3. +3 is higher. So this becomes ferrous, Ferrous chloride. Okay. And the other one is ferric, Ferric chloride. Okay. So ferrous relates to lower oxidation state. Ic relates to a higher oxidation state. Now we have another one. Let's look at an example where if the example is saying stannous, STANNOUS, stannous sulfide, SULFIDE. The other one is Stenic sulfide. All right, so stannous, OUS, ic. So sulfide, that means it's just a sulfur. Okay, so write down this. Sulfide is just sulfur. Sulfide is just sulfur. Stannous, SN, that's the formula. SN, that's the formula. Okay, and this relates to tin. Tin is SN. Okay, now same thing, group number and the charges. Group number and charges. Group number, charges. Now, group number, tin. Tin is in D block. Okay, so that is why it's in D block. So always check the table, periodic table. So tin is in D block, or you know, it has a D, D in it, D orbital. But if you look at it, it's in the on the metallic side, and then also check for the table. So yes, tin can have +2 oxidation state, and tin can have +4 oxidation state. So +2 oxidation state is the state in, which relates to a lower oxidation state, +2. Stenic relates to a higher oxidation state. So always check the table on more than 1 positive charges. So there you can get this information. Anyways, so sulfur belongs to group 6A and the charge is -2. 6A and the charge is -2. So now just write the formulas. So we have Sn +2 and sulfur -2. We have Sn +2 and Sn +4 and S is -2 and crisscross. So this number comes here and this number goes here. This number comes here and this number goes here. Okay, so now what do you get? You get Sn, remember, +2 and -2 cancels out. And you need to simplify it. That is why, you have to cancel it. So +2, So now it becomes Sn 2S2 and it cancels out and the whole thing is SNS. The other one is Sn 2 comes here and Sn 4 comes here, but you need to simplify. So when we simplify, 2 and 4 cancel out and we get SNS2. Okay, so the name is tin 2 sulfide. The other one is tin 4 sulfide. Okay, so these are, you can get them with the practice, know the symbols, know the names, so those things. Next is, let's do with the polyatomic ions. So with polyatomic ions, the name remains as it is. Like for example, sodium, or let's do another one, potassium carbonate. So for the potassium carbonate, you are going to always check, let me write this in red. So you should either, so here's the thing, either memorize the polyatomic ions with charges and the symbols, or check. It's not either, you have to memorize, and then always check so you don't make a mistake. Always check the polyatomic ions tables. Okay, so you don't. So we see in the polyatomic ions table, carbonate is CO3 -2. And potassium stands for K. So same story, group number, charges. So potassium is in a group number 1A, charges +1. So here is this +1. And carbonate is what it is. You just copy the carbonate the way it is. Then crisscross. This number comes here and this number comes here. And remember, we do not write the subscript. So basically these are all subscripts. Subscript for 1. Leave it, ignore it. So what do you get then? The formula becomes K2CO3, and that's it. So the name is potassium carbonate and the formula. Okay, let's do another one. 7. Okay. All right. Let's do the thing is calcium phosphate. Calcium phosphate. So same thing, you should know the symbol for calcium. Symbol for calcium is Ca. And from the polyatomic ions, phosphate is PO4 minus 3. Okay, calcium is in group number 2A. So therefore the charge on calcium is +2. So calcium is +2. And the rest is just crisscross. This number comes here and this is here. So because 2 is more than 1, therefore PO4, polyatomic ion, is kept in parentheses. Okay, so we get here Ca3, okay, that number came, parentheses, PO4 whole twice. That's the formula. Okay. All right. Let's do 8. Then comes 9. Next is let's do copper. Two or copper 1. Nitrate. And here you have copper 2 nitrate. Okay, so copper 1 means copper plus 1 state. Copper 2 means copper plus 2 state. Nitrate stands for NO3 minus 1 state. So this is the, again, you have to check. You should memorize, but you check the polyatomic ion table. So this goes here, and this number comes here. This number comes here, and this number comes here. Okay, so then we see that the name here, +1 and -1 cancel out. So what's the formula then? Ca cancel. So here we have CuNO3. And this, the name also is because it's a lower oxidation state. So this is cuprous, CuPROUS, nitrate, NiTrate. Okay, the next is Cu, okay, parentheses, because for 1 we don't write. So I'm not going to repeat that again and again. NO3 whole twice. Because 2 is more than 1, therefore nitrate is put in the brackets. Okay, so but the name is cupric, CuPric, nitrate, because it's a higher valence state. All right, let's look at one more, 10th example. And that is, let's say, lead. Lead 2. Sulfate, or let's do this, phosphate. And lead 4, phosphate. Okay, so here lead is Pb. 2 means +2. Phosphate is PO4 minus 3. Here lead 4 is Pb plus 4. Phosphate is PO4 minus 3. And now you crisscross. 2 comes here and 3 goes here. 4 comes here and 3 goes here. So what do? When 2 and 4 are more than, it's more than 1. So therefore, you will have to put them in parentheses. So this becomes Pb 3 parentheses PO4 whole twice, because 3 and 2 cannot further be simplified. And the other one is Pb 3 parentheses PO4 whole 4. Okay, and 3 and 4 cannot be simplified. So you see that? And it's more than 1. 4 is more than 1. Therefore, you put phosphate in the parentheses. 2 is more than 1. So you put phosphate in the parentheses. So this means this. So this name is plumbous, P-U-L-E-M-B-O-U-S, plumbous phosphate, a lower oxidation state, plumbous phosphate. And this is plumbic phosphate, plumbic phosphate. Okay, so all of this is going to come through practice. Now let's look at the nomenclature where we covered the binary ionics. We covered the naming which relates to the these polyatomic ions and the numbers with and the other ones, with the variable valence state. Now we are going to look at the hydrates and the let's do the hydrates. So now we have, so these are just, let's look at the naming nomenclature names of the so this is binary ionic. Then we have the variable valence. Okay, so by variable means more than one positive charge. More than one plus charge. And we have polyatomic ions. So, okay, so this is the this is what we did just now. 3 sets we did. Now, and let me just put this here in this number A. Okay, next is writing the formulas with the let's do the hydrates and hydrates, or let's do first with the covalent compounds. Covalent compounds. Okay, covalent compounds. Okay, so for the covalent compounds, like for example, you have, for example, it's very easy, carbon with 1 oxygen. So this is carbon. Oh, I think I did not, did I put this here? 1 second, maybe I forgot it here. Roman numerals, non-metals. Oh, we covered this, why they do that. Electronegativity, polyatomic ions we did, non-metals. Oh, here they are, without the charges, mono, di, tri, tetra. This is what is going to be used. So we will do carbon, the first letter, the first element, the name does not change. So first element, name as is. The second one, second element, you get the mono, di. So this is the first element. This is generally, not all the time, So, or in other words, Let's put it this way. Okay, when the first element is there, if first element is only one, then name is as is, then name as is. So don't put mono, right? Don't put that. Then next is the second element gets the second element is, you know, a mono, di, tri, tetra, those things. Mono, di, tri, tetra, etc. Okay, so here we have carbon, just one, but oxygen is also just one, but we call it carbon monoxide. So don't put two oxygens, like two O's, just two. But if you have carbon with two oxygen, then it becomes carbon, the name just as it is, carbon, this becomes dioxide. And dioxide, oxygen is small, oxide, O-X-I-D-E. Okay, next is if you have carbon with chlorines, and there are 4 of them, then this becomes carbon, the name as it is. And since there are 4 chlorines, this becomes tetrachloride. Okay, next is, for example, you have sulfur with 3 oxygens and sulfur with 2 oxygens. So this is sulfur and sulfur, that name doesn't change, that remains the same. This becomes trioxide and that becomes dioxide. Okay. On the other hand, if you have nitrogen 2, oxygens 5, then this becomes dinitrogen. Dinitrogen pentaoxide. Okay, pentaoxide. So these are just a commonly, you know, we get these names. Now let's look at the third piece, which is, let's see if there is something else. Yeah. Okay, next is C. And that relates to the hydrates. Hydrates means water molecules are attached to ionic compounds. So hydrates. So hydrates are some number of water molecules attached to ionic compounds. And which ones are those? Those are ionic compounds, and those are like Cu, SO4, 0.5 H2O. So there are 5 water molecules attached. So what will you name, or how will you name this? This is copper sulfate penta, because there are 5. Penta means 5. Hydrate, because there are 5 water molecules attached to one molecule of copper sulfate. That's what it means. Okay, let's get one more. Another example is the, like magnesium chloride, Mg Cl2 0.2 H2O. So this becomes magnesium chloride dihydrate, 2 water molecules. All right, so those things. And the last one is the D, which is the acids. So here we have acids. Okay, acids such as the hydrogen with fluorine, aqueous. Hydrogen with chlorine, aqueous. Hydrogen with bromine, aqueous. Hydrogen with iodine, aqueous. So hydrogen with fluorine is in the aqueous medium. In the aqueous medium, it is hydrofluoric IC acid. Okay. And the other one is hydro. Hydro is attached to all of them. Acid is attached to all of them. Fluoric, this is chloric. This is bromic. And this is iodic acid. Okay, so this is one piece. Next is if you have HCl in a gaseous phase, if you have HBr in the gaseous phase, then their names are hydrogen chloride. Okay, and this one becomes bromide. So pay attention. So this is in the gas phase. When they're in the gas phase, then it's the hydrogen chloride and bromide. Okay, next is the acids such as other acids. You just have to remember them. HNO3, H2SO4, okay, H2SO3, sorry, one second, HNO3 and HNO2. So higher oxidation state is nitric, NiTric, nitric acid. The lower oxidation state, nitrous acid, OUS. Okay, next is, for example, H2SO3 versus H2SO4. H2SO3 is sulfurous, OUS, sulfurous acid. And this one is sulfuric, SULFURIC acid. So pay attention to higher oxidation state is ic, lower is us. Us is lower, higher is ic. Okay, so here this one was the gas phase, and these are the aqueous medium. So this is, let me just put this here. These happen in water, or this is also called the aqueous, AQUEOUS, aqueous medium. All right. Besides that, this is another thing is this, for example, HClO3, HClO4. Okay, so this becomes, this is chloric acid. This is chloric acid, but this is perchloric acid. Remember the perchlorate ion. So this is perchloric acid. And similarly for the hypochloric and hypochloric, wait a minute, chlorous, yeah, hypochlorous acid. Okay, so these are the basics, and you can here leave out optional, or optional, the on worksheet. What is optional worship? Organic namings, organic compounds. If you do it, it's fine, it's good for you, but I'm not, if you have time, you can do it. But it's not like I'm going to give extra credit or something, but that's, what it is. Okay. I hope that was easy. And if you guys have any questions, please don't hesitate to ask me. Okay. Anytime you can just post in your questions and I'll be happy to help you. All right. Okay. Thank you. Take care. Bye-bye.